Hi future GISPs. I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to spend years reading textbooks, getting degrees, paying for prep courses, and searching the internet for information like I did. In this video, I'm going to teach you everything I learned about analytical operations and methods. Analytical operations and methods is the third section under the Analytical Methods category of the GISCI Geospatial Core Technical Exam list of knowledge categories. Let's get started with section 603, Analytical Operations and Methods. Spatial data analysis. Spatial data analysis involves studying the characteristics of places and the relationships among them. Spatial analysis is used to determine relationships, detect patterns, assess trends, and make predictions. Geoprocessing. Geoprocessing involves performing operations that transform, analyze, and manage data. Spatial overlay analysis. Overlays are the combination of spatial and attribute data from two or more spatial layers that cover the same area to study the relationship between them. Layers should be in the same coordinate system for a spatial overlay analysis. Raster layers should have the same cell size to perform an overlay. Overlay analysis methodology. Overlay analysis methodology evaluates how features overlap to answer problems. Overlay analysis is based on Boolean logic. The fundamental overlay analysis workflow is: define a problem, break the problem into submodels, determine significant layers, reclassify or transform data within layers, weight layers, add or combine layers, and analyze the results. A bounding polygon. A bounding polygon is a polygon that is used to determine the presence of features in a specified area in a spatial overlay operation. Spatial overlay tools used in spatial analysis include append, buffer, clip, dissolve, erase, identify, intersect, union, symmetrical difference, and update. Append. Append adds data from one dataset to another. Buffer. Buffer creates polygons around input features to a specified distance from those features. Clip. In a clip function, features and parts of features that are located outside the bounding polygons are erased. A clip produces the same result as an intersect followed by an erase. Dissolve. Dissolve combines features with matching attributes. Erase. In an erase function, features and parts of features from the input class that aren't coincident with the bounding layer are output. Identity. In an identity function, input features are split by overlay features. Only input feature areas are output. Intersect. In an intersect function, only features and parts of features common to all input layers are output. An intersect is like a spatial AND. Union. In a union function, input features are combined with bounding features. A union is like a spatial OR. Symmetrical difference. In a symmetrical difference function, features common to either input layer or overlay layer, but not both are output. A symmetrical difference is like a spatial exclusive OR. Update. In an update function, input feature geometry is replaced by the update layer. Vector overlay. Layers must be projected to the same coordinate system to perform a vector overlay analysis. Computationally, a vector overlay identifies line intersections. Vector overlay typically outputs the lowest dimension features. Vector overlay can be quite time-consuming and require significant computational resources. In a vector overlay, each line segment must be checked against every other line segment. That's just how computers work. The common feature problem. The common feature problem occurs when the same features occur in multiple overlay layers and different representations of the same phenomena occur. Common polygons can cause sliver polygons in a polygon overlay. Sliver polygons. Sliver polygons occur when the same boundaries occur at different locations in different layers. Sliver polygons are a problem because they use storage space, slow display speed, and slow analysis speed. Solutions to sliver polygons include using the boundary with the highest accuracy, manually identifying and removing sliver polygons, and defining a greater snap distance during overlay. Proximity analysis. Proximity analysis involves performing analysis using buffers. Buffers are used to determine which features are located within a specified distance of other features. There are different types of buffers. Types of buffers include a standard buffer, a simple buffer, a compound buffer, a nested buffer, and variable distance buffers. Buffer. A buffer is a polygon that is created by specifying a distance from a feature or set of features. Simple buffering. A simple buffer identifies an area that is within a fixed distance from a set of input features. Boundaries of buffer polygons created around different features are dissolved in simple buffering. Compound buffering. Compound buffering maintains the overlapping boundaries of buffer polygons created around different features. Nested buffering. Nested buffering creates multiple buffers at multiple distances from features. Variable distance buffers. In variable distance buffers, buffer distance from features are different for different features or different attribute values. Spatial interpolation. Spatial interpolation is estimating unknown values at unmeasured locations using known values from measured locations. Global interpolation. Global interpolation uses all known points to define an unknown value. Local interpolation. Local interpolation uses a sample of unknown points within a specified proximity to estimate unknown values. Nearest neighbor interpolation. Nearest neighbor interpolation assigns the value from the nearest observation. Nearest neighbor interpolation is also known as Thessian polygon interpolation. Nearest neighbor interpolation creates Thessian polygons. Thessian polygons. Thessian polygons divide a plane into polygons classified by the closest point. A Venori diagram. A Venori diagram is a visual representation of Thessian polygons. Fixed radius interpolation. In fixed radius interpolation, values are estimated based on the average of values within a specified distance of the location. Fixed radius interpolation tends to smooth the sample data. A larger search radius smooths the data more. Natural neighbor interpolation. Natural neighbor interpolation weights nearby samples based on their sizes or areas. Natural neighbor interpolation is also known as area stealing interpolation. Inverse distance weighting interpolation. Inverse distance weighting interpolation averages sample data points in the neighborhood of the processing point. More weight is given to closer points. Less weight is given to points further away. Inverse distance weighting interpolation will smooth out a surface. It does not preserve all of the data points. Inverse distance weighting interpolation works best with evenly spaced data. Geostatistics. Geostatistics was originally developed to predict probability distributions for mining operations. Geostatistics is related to interpolation methods, but extends beyond simple interpolation. Geostatistical techniques rely on statistical models that incorporate random functions. Geostatistics incorporates the uncertainty associated with spatial estimation and simulation. Kriging. Kriging is the centerpiece of geostatistics. Kriging has three main components: spatial trend, local spatial autocorrelation, and stochastic variations. Spatial trend is the increase or decrease depending on direction. Local spatial autocorrelation is the influence of nearby known values based on their distance to the predicted location. Stochastic variations are the randomness inherent in nature. Kriging is a statistical interpolation method. It provides an optimal prediction surface and delivers a measure of confidence in how likely the prediction surface is to be true. Kriging is based on Tobler's first law of geography. Kriging can be done if the data has a normal distribution, is stationary, and doesn't have trends. Kriging is a good choice for datasets with clusters of data with no points in between. Kriging relies on a semivariogram. Points in the search radius are weighted based on the autocorrelation in the semivariogram. The resulting surface from Kriging is checked with cross-validation. A root mean square error can be determined from the summary table. Kriging takes a significant amount of computational processing power. Kriging components include a variogram, a nugget, a sill, lag distances, lag tolerances, a range, and co-kriging. A variogram graphs the autocorrelation of values with the semivariance on the y-axis and the range or distance on the x-axis. The nugget of a variogram is the semivariance at the smallest range observed. The sill of a variogram is where variation levels off and autocorrelation becomes no greater than random on a semivariogram. Lag distance is the distance between a pair of points. Lag tolerance is the lag distance at which a pair of points are influenced by covariance. The range is the distance at which the sill is reached. Co-kriging is kriging with two or more variables. In co-kriging, the variables are weighted. Spline interpolation. A spline was a flexible ruler that was used by draftsmen to create smooth curves through a set of points. Spline interpolation estimates values using a mathematical function that minimizes the overall surface curvature, resulting in a smooth surface that passes through the input points. Spline functions are a set of joined polynomial functions that are fit to short segments. Higher order polynomial functions create a more uneven surface. A trend surface. A trend surface does not pass through measured points. There is an error at each sampled location. Trend surfaces are best used for representing smoothly fitting surfaces. Trend surfaces are not good at representing highly convoluted surfaces. Interpolation accuracy. The accuracy of an interpolation can be assessed by comparing interpolated values with actual measured values. Tools for assessing interpolation accuracy include cross-validation, root mean square error, and mean absolute error. Cross-validation removes a point from input data, runs the prediction for that location, and records the difference between the input and the predicted value. Cross-validation iterates through all of the input points and creates a summary table of residuals, comparing the actual values versus the model's predicted values. The root mean square error is the square root of the average of square distances between the interpolated and actual locations. Mean absolute error is the average distance between the interpolated and actual locations. It's less sensitive to outliers than the root mean square error. Mean absolute error doesn't square the errors like the root mean square error. Spatial prediction. Spatial prediction estimates unknown values based on a statistical fitting process rather than an algorithm. Spatial prediction is more complex than interpolation. Spatial prediction incorporates additional variables. Hotspot analysis. Hotspot analysis identifies statistically significant clusters of high or low values using the GEDIST or G statistic. A high z-score and small p-value for a feature indicate spatial clustering of high values. A low negative z-score and small p-value indicate a spatial clustering of low values. The higher or lower the z-score, the more intense the clustering. A z-score near 0 indicates no apparent spatial clustering. Kernel density mapping. Kernel density mapping uses a set of sample locations to estimate a continuous density surface. It applies a kernel function on each observation and spreads the observation over the kernel window. Samples can be lines but are usually points. The kernel density estimate at a location will be the sum of the fractions of all observations at that location. Kernel density mapping is used for point or line data smoothing, risk mapping, and hotspot analysis. Density. Density is the amount of features per area. Viewshed. A viewshed is the geographical area that is visible from a location. Reverse viewshed analysis. A reverse viewshed analysis is the determination of an area or places from which a point can be viewed. Line of sight. Line of sight exists if a visual connection between 2 points is possible. Terrain analysis. Most terrain analysis are performed using a DEM or raster data model. Raster datasets facilitate the easy calculation of slope, aspect, and other terrain variables. Z-values are required for terrain analysis. Usually, mathematical operations are applied to a moving window on a raster dataset in terrain analysis. Fundamental terrain analysis functions include height, slope, aspect, upslope area, flow length, upslope length, profile curvature, and plan curvature. Height. Height is the distance above a base. Slope. Slope is the rise relative to horizontal distance. Slope percent equals the rise divided by the run multiplied by 100. A slope of 0 is flat. A slope of 100% is vertical. The tangent trigonomic function is used to calculate slope as degrees from 0 to 90 degrees. The 4 nearest cell and third-order finite methods are most commonly used for the moving window. Aspect. Aspect is the downhill direction of the steepest slope. Aspect is used to determine what direction water will flow, how much sunlight an area will receive, and what portion of the terrain is visible. Aspect is typically reported as an azimuth angle from 0 to 360 degrees. Flat areas have no aspect and no downhill direction. The 4 nearest cell and third-order finite methods are most commonly used for the moving window. Upslope area. Upslope area is the watershed area above a point. Flow length. Flow length is the longest upstream flow path to a point. Upslope length. Upslope length is the total upstream flow length that flows to a point. Profile curvature. Profile is the terrain curvature parallel to slope direction. Profile curvature is the index of the surface shape in the steepest downhill direction. Plan curvature. Plan curvature is the terrain curvature perpendicular to slope direction. Concave. Concave terrain is a bowl-shaped path. It has small or negative values. Convex. Convex terrain has a peak-shaped path. It has large or positive values. A moving window. A 3-cell by 3-cell window is most common. Morphometric analysis. Morphometric analysis correlates parameters that define drainage basin characteristics and basin hydrology. Terrain elements in morphometric analysis include plains, peaks, passes, saddles, channels, ridges, and pits. Hydrologic analysis. In hydrologic analysis, spatial functions are applied to DEMs to yield information about hydrology. Hydrologic analysis calculates hydrologic parameters such as watershed. A watershed is an area that contributes flow to a point on the landscape. Watersheds are also called basins, contributing areas, catchments, drainages, subbasins, and subcatchments. Flow direction. Flow direction calculates the flow from a cell to an adjacent cell. Flow direction is stored as compass angles in a raster. Flow direction is expressed in degrees azimuth or in a directional number towards the adjacent cell. A drainage network. A drainage network is a set of surface cells through which water flows. It is based on a flow direction surface. Flow directions determine where streams and rivers are located. The specific catchment area, or SCA. The specific catchment area is the total area draining to a point divided by the cell width. The stream power index, or SPI. The stream power index is used to define the potential erosion energy at a point. The stream power index depends on the upstream area and local slope. The stream power index equals the specific catchment area multiplied by the tangent of the slope to the point. Profile plot. A profile plot displays elevation against distance in a graph. Profile plots are useful for viewing elevation change and distance along a path. Profile plots are used in terrain and hydrologic analysis. Raster resampling. When processing multiple raster datasets, cell resolution should be the same. If they aren't the same, some may need to be resampled to allow processing. Raster resampling methods include nearest neighbor resampling, majority resampling, bilinear interpolation, and cubic convolution. Nearest neighbor resampling assigns the value from the cell with the nearest cell center. Majority resampling is the majority value out of the nearest 16 cells. Bilinear interpolation is the weighted average from the cells with the 4 nearest cell centers. Cubic convolution is the weighted average from the 16 cells with the nearest cell centers. Model Builder. Model Builder in ArcGIS Pro is the most popular software used for designing and performing spatial analytical operations. It's used to create custom workflows by chaining geoprocessing tools. Model Builder is used to design flowcharts of operations. Network analysis. Network models are used to analyze cost, time, delivery, and accumulation of resources along links and between centers. Resources flow through the network and may be generated and absorbed. Links are routes through which resources can flow. Centers are connected via network links. Types of network analysis include transit cost, route selection, resource allocation, and traffic modeling. Transit cost analysis analyzes the cost of moving a resource through a network. Route selection analysis identifies the best route based on specified criteria. Route selection involves an algorithm that recursively follows a least cost set of arcs. Resource allocation analyzes the apportionment of a network to centers. Centers can have center capacities and maximum ranges. Traffic modeling. In traffic modeling, streets have attributes such as speed, direction, capacity, and cost. Bottlenecks, transit times, and underused routes may be identified through traffic modeling. Spatial scope. The spatial scope of an operation can be local, neighborhood, or global. Local operations use only the data at the input location. Neighborhood operations use data from the input locations plus nearby locations. Global operations use data from the entire input layer. Set algebra. Operations are performed on sets of numbers in set algebra. Set algebra is not inherently a spatial analysis, but it can be used in map algebra. Boolean algebra. Boolean algebra uses logical operations on variables that produce truth values. The truth values are true and false. Boolean algebra uses logical operators such as conjunction, known as and, disjunction, known as or, negation, known as not, and exclusive or, known as XOR. Logical operators. Logical operators are symbols or words that connect two or more expressions and return a value of either true or false. The symbols used to represent logical operations are different in different programming languages. Geocoding. Geocoding is the process of spatially referencing point features based on the address of the feature and knowledge of an address range for the linear network. The estimated location of geocoded addresses are based on linear interpolation. Address ranges are assigned ordinally, while geocoding is an interval estimate. This can cause problems and inconsistencies. Geocoding is also called linear referencing. Point pattern analysis. Point pattern analysis studies the spatial distribution of points. Point pattern analysis uses various methods and measurements, such as density-based methods and distance-based methods, to analyze, model, visualize, and interpret the properties of point patterns. Characteristic Hall polygons. Characteristic Hall polygons are special bounding polygons that are created by constructing the Delaunay triangulation of a set of points and then removing a subset of the resulting triangles. The largest triangles can be discarded, leaving a smaller area than a convex hull that contains all of the points. A convex hull. A convex hull is the smallest polygon that completely encloses a set of points and for which all exterior angles and edges are greater than or equal to 180 degrees. Concave hull. A concave hull is the smallest polygon that completely encloses a set of points. Core area mapping. Core area mapping involves mapping the primary area of influence or activity for an organism, object, or event. The core area represents a central or important region where features occur frequently. Core area mapping is often used in crime hotspot analysis. Core area delineation. Core area delineation identifies core areas dependent on the selected bandwidths. Time series analysis. Time series analysis studies changes over time using spatiotemporal data. Time geographic density estimation. The time geographic density estimation estimates the area that a tracked object could have traveled in between tracked locations. Time geographic density estimation depends on the time between observations and the maximum velocity of objects. Time geographic density estimation results in an ellipse around the location points. As the interpoint distance approaches the maximum velocity, the ellipse becomes narrower. Spatial statistics. Spatial statistics is used to calculate statistics related to spatial patterns and distributions. Python scripting. Python scripting is used to write scripts for custom analysis workflows. You can also see Section 605, Knowledge of Descriptive and Spatial Statistics, for more about spatial statistics. You can also see Section 802, Coding, Scripting, and Modeling Basics, for more on Python coding. Now you know everything I learned about analytical operations and methods to easily pass the GISP exam. Wow, several complex topics were mentioned in this section. Spatial analytics is not an easy subject to learn. Fortunately, you don't have to be an expert on all of the topics mentioned in this section to do well in the exam. You do have to be able to understand the concepts discussed in this section. You do not have to memorize formulas or be able to actually perform these types of analysis during the exam. Don't forget to thumbs up and subscribe to my channel so that I can keep helping people pass the GISP exam and achieve the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is an easily understandable, comprehensive, graphical, all-in-one resource for passing the exam. You can find the link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.